Well, hello everyone. This particular Zoom lesson is a replacement for our 9 o'clock Friday one that I wasn't able to appear on. And there are really only two questions, but they're fairly long that we need to cover. And the first one I'm going to do is find the power series for this function. Now, trying to find the power series is a little bit tricky when the only guy you've got in town that you know how to find power series are fractions. So this question doesn't really get into the details of how you're going to do that. So essentially what I'm going to do is I am going to find the power series for that guy. That I know how to do. And then I'm going to look at that and I'm going to say, aha, if you integrate this, you'll get something that looks very like that. And therefore I should be able to get the power series of this guy by using the integral of this fellow's power series. So before I get into the details of that, let's integrate this guy. He is equal to, since hopefully you recognize that guy, it's going to be the natural log of 9 minus x with a little -1 tagged on at the end, plus a c. Are we good with that? So if I rearrange this a little bit, essentially what that tells me is that the natural log of 9 minus x is c, because I'll put that first, take away the integral of this guy. So now our job is first to find the power series for that, check. Then integrate it, yep. Then make it a negative, and then stick a c at the front. And later on we'll talk about what that c is equal to. It's essentially going to be the value of the function when x is 0. So I can tell you it's going to be a ninth just by looking, or at least a log of a ninth. So rearrange this guy by pulling out 9 as a common factor. We've got that guy. I recognize this fella. This fella we can do, because it's sigma, n equals 0 to infinity, would be x to the n, but in this case, 1/9 to the n. So I now have n equals 0 to infinity, 1 to the n on top, which is just 1, 9 to the n on the bottom. And if I feed this one in, what I'm essentially going to do is just add another 9 to the bottom power. And so I now have that guy. Okay, now, this fella should be x. So, plot in time, you get x to the n. So, that guy, x to the n, square the top and bottom, combine the 9s, you've got that. So I have 1 over 9 take away x is n equals 0 to infinity, x to the n over 9 to the n plus 1. If I take the natural log, if I take the integral of that, I should be able to integrate this guy as well. Now you can switch the sigma and the integral around, and if you think about that, it really just means you can integrate each term individually. So add 1 to the power and divide by the new power, plus a c. So the integral of this guy ends up being this fella. So far, so good. Now, we know what we get when we integrate that. We get this fella. We get negative the natural log of 9 minus x. And so that's going to be equal to n equals 0 to infinity. This fella. If you distribute a negative through both sides, you basically get negative this guy. Yes, you could say you're subtracting an unknown constant, but if it's an unknown constant, you can just call it C. Now, I need to know what C is equal to. Well, if you make x 0, what you get is C take away a whole load of zeros all added together. And that means that the log of 9 is what C is equal to. So we are now kind of finished this part of the puzzle. We have n equals 0 to infinity, a C, which is what? Log 9. Take away this guy. Just rewrite this guy a little bit clearer. The natural log of 9 minus x is C, which is natural log of 9, subtract from n equals 0 to infinity, x to the n plus 1 over n plus 1, 9 to the n plus 1. And we're essentially done. Now, you're meant to calculate R and I, the radius and the interval of convergence, essentially for this power series. So I'm only going to focus on this piece, not worry about the negative or even the log 9, because they do not affect the radius or the interval of convergence in any meaningful way. So the limit as n tends to infinity of this ratio. Should always keep the absolute values in these situations. Add 1 to that gets you n plus 2. Add 1 to that, so n plus 1 more, gets you n plus 2. And 9 to the n plus 2. Then you have this fella, all over this fella. So what I'm going to do, see if we can tidy up some bits and pieces. This cancels with this and leaves a 9 on the bottom. This cancels with this and leaves an x on the top. So we are now looking at n plus 1 over n plus 2, x over 9. So far, so good. Now, this fraction here, the limit as n tends to infinity is 1. You can prove it by L'Hopital or by dividing top and bottom by n, but the bottom line is that's what you get. 1 times that gets you that. Now, for this to converge, according to the ratio test, this fraction has to be less than 1, which becomes that guy. So the radius of convergence is 9. The interval of convergence is going to be in that range, but it may or may not use the endpoints, which means we have a second extra piece of work, and that is to look at the endpoints. That's at -9 and at 9. Now, if you plug in x equals -9 into this power series, you get n equals 0 to infinity. And I already know this isn't going to work, but there's the x, there's the n plus 1, there's 9 to the n plus 1. And you basically get a version of the harmonic series. I could prove this by doing a comparison or a limit comparison test to a P series, P equals 1. But the bottom line is it diverges. And if you try, sorry, that was plus 9 I just did. If you try negative 9, you get this fella. And you get negative 9 to the n plus 1 over n plus 1 to the n plus 1. And you could go and do a whole load of stuff. I'm going to kill that one for a different reason. It's meant to be representing this function, right? So you know that when you choose this guy, you're basically going to get the log of 18, which I know it does exist. But to continue the process from n equals 0 to infinity, if you take this guy and that guy, you basically get the powers of 9 cancelling. And you end up with an alternating series that looks like that, which converges. So I knew it should converge, and it did. So what does that tell me? That my interval of convergence is you can use, get it right around, you can use negative 9, so square brackets, but you can't use positive 9. And that is the end of that question. So the next and final question that I want to do is finding the power series for a function that is of this format. So this is question 7. We're going to be using Desmos at the end of this. So I have x to the 5 over x to the 4 plus 1. If I rewrite this as x to the 5 times 1 over 1 plus x to the 4, I can recognize that this here is basically sigma 1 plus x, where the x is going to be replaced by x to the 4. So you get n equals 0 to infinity, negative x to the 4 to the power of n. And that becomes x to the 5 multiplied by negative 1 to the n, x to the 4n. And that gets you n equals 0 to infinity, negative 1 to the n, x to the 4n plus 5. And if you go and essentially find the radius of convergence, you're going to get, the answer is 1. And if you find the interval of convergence, you find that that's going to happen. So the only thing I want to do with this question is to show you that this power series here is a very close approximation to that guy. It's only going to be of any use in this range, right? So I don't want to make it, so when I draw my little sketch on Desmos, I'm going to kind of try and stick to somewhere like that. I'll probably move in a little bit either side just to avoid this number here especially, which is a problem because I know they're vertical, well, it's maybe not vertical as today. But let's move over and see what does that look like when you set up Desmos. So I have to get Desmos on my screen. I know you're hiding here somewhere. Where are you, Desmos? There you go. Okay. So here it goes. That's funny. There it is. So I'm assuming that you're losing Desmos, but I'm going to go out and in just to be really safe, because since there's nobody here to tell me that it's really there, I can't be 100% sure. So in this one, I am going to put f of x. And that was x to the power of 5 divided by x to the power of 4 plus 1. So let's just zoom in, because I'm only interested in -1 to 1. Since that's the interval of convergence, what that says that the power series only truly can guarantee to work in this range. So I'm not going to type in an infinite polynomial because that just isn't practical, but I can plug in a few terms. So if I plug in 0, for instance, I will get x to the power of 9, x to the power of 5, I should say. So y equals x to the power of 5. And that's my first fit. Now, that's just the first term. I'm now going to do two terms. So that's the first term. If you plug in n equals 1, you get -1 x to the 6. So you get basically negative x to the 6. And I don't know how we can hide this. I know you can hide things. So if I hide that one, there we go. Can you see? Maybe I should change my window a little bit. Since I'm only interested in from here to here, I only really need to go -2 to 2 for the y. So let's zoom in. Right, and I'll change the y values from -2 to 2. And that way, we're only really focusing on what matters. Okay. Would you agree it's a pretty good fit? If I put the first one in, do you see the blue one's not quite as good? The green one's a little bit better. If I put in a third term, that ends up being add x to the 7. If I put in one last one, that's take away x to the power of 8. Now, what you can do if I just take these guys out, can you see the original and the red one? The red one, I should say, is the original, and the black one is our guy. Now, if I zoom in, you see it's really good to almost 0.5, right? It starts drifting a little bit. If I zoom in to like the 0.4 mark, would you see it's pretty much on top of it? If I zoom in to the 0.2 mark, you see you can't really tell the difference. Have I convinced you that this function can be represented by that guy? Now, I'm going to see if I can add in a few more just to see the pattern. That's when you add 9, then you take away 10, then you add 11, and then you take away 12. And I've got a load of capitals, I didn't realize that. So let me fix that. There's an X. There's an X to the 10. There's a X to the 11. There's an X to the 12. Now, the benefits that you're getting by adding more and more terms is getting less and less helpful. You see this one here? I went all the way to x to 12, and I guess the only real benefit I got was it traveled a little bit further closer to the 0.5s. What I could have, however, do theoretically, couldn't I do this for infinity? And if I did it for infinity, it would be a perfect match. And that's pretty much all I want to do on that question. Just double check that I've covered everything that you need for your homework. So that's essentially question 7. Question 8 we did in class, and that was essentially showing that e to the x works. Question 10 is a video that you watch, and I'll let you enjoy that.